Good morning, Math HL students. This is our remote lesson 7. We're going to continue our conversation about numerical solution to differential equations. Let's review what we've learned last class. So, as I said, numerical analysis or solving things numerically, especially differential or partial differential equations, is like the whole of math. That's almost all of applied math. It's that and modeling. But we're going to solve a particular type of order differential equation. It's explicit, so y prime of x equals a function of x and y, and you're given an x sub naught and y sub naught, and suppose the true solution is in blue. So let's review what Euler's method is. All right, I have this picture here, and I'm going to kind of explain what it means. So the true solution is in blue. X sub naught, x sub 1, x sub 2, x sub 3 is our values of x. All right. You know x sub naught, y sub naught, so you know the first point and you know for sure that it is part of the solution. So in order to find the second point, the first thing you do is draw a slope at x sub naught, y sub naught, or a tangent line at that point, and you find the slope of that tangent line. Well, what's the slope of the tangent line if you don't know anything about the function? Well, you actually, because you have a differential equation, you do know the slope of the function at point xy. So the slope of this line, m sub naught, is big F evaluated at x sub naught, y sub naught, and then the equation of the tangent line is m sub naught times h plus, or rather the value of y sub 1 is m sub naught times h plus y sub naught, right? So that should give you x sub 1, y sub 1. Now notice y sub 1 is already not on the curve, right? So every y value after y sub naught is an estimation. Every slope after m sub naught is an estimation as well, because the first step already throws you off the curve. All right, and then we'll do the same thing again. M sub 1 is the slope of the second. M sub 1 is the slope if the function passed through x sub 1, y sub 1. So it's an estimation of the slope. You can see here that it kind of generally is moving in the same direction as the curve does, but not obviously exactly. And then so that's m sub 1, and then x sub 2, y sub 2 is the Euler iteration. M sub 1 times h. 2 is f evaluated at x sub 2, y sub 2. Again, x sub 2, y sub 2 is an estimation, right? So this is where the real value of y is, and this is the estimation. So so basically you get, but do you see m sub 2, the slope of this line is in the same direction as the curve, and then y sub 3 is m sub 2 times h plus y sub 2. Okay, so that's Euler's method. That's Euler's method. You find the slope, and you basically find the equation of a line, right? So that's Euler's method. It's right here. Y sub I plus 1 equals m times h plus y sub I. Okay, Euler's method. And then the intervals are the same length. All right. And then we said there's something called improved Eulers. Improved Eulers. So improved Eulers, instead of finding one slope to get to the next y, you find two slopes. So m sub 0, okay, so you're finding two slopes. The first slope is 1, the second slope is 2, but they both take in x sub naught, y sub naught, so this is going to be m sub naught 1, m sub naught 2. To find m sub naught, you evaluate it at x, so this is m sub naught, you evaluate the slope at x sub naught, y sub naught. To find m sub naught 2, you evaluate the slope at x sub 1, which is x sub naught plus h, this is just x sub 1, comma. Now you don't know y sub 1, so we replaced y sub 1 with Euler's estimation of y sub 1, which was y sub naught plus h times m sub naught 1, right? So that's m sub naught 2. So y sub 1 was y sub 0 plus the average, h times the average of the two slopes. So this what, right? X sub 1, y sub 1. Y sub 1, the average of the two, the slope of the red line is the average of the two purple slopes. All right, and then we do the same thing, m sub 1, 1, m sub 1, 2, so it's m sub 1, 1 is f evaluated at x sub 1, y sub 1. F sub 1, 2 is f evaluated at x sub 2 or x sub 1 plus h. Y sub 2, you don't know yet. You're trying to find it, so you estimate it with Euler's method. So y sub 1 plus h times f sub 1, y sub 1. And that's your y sub 2 is y sub 1 plus, right? So the slope of this line is the average of the slope of these two purple lines, right? Okay. And then you do the same thing again. Make sure everything's correct here. Yeah, okay. You do the same thing again. So you get x sub 3, y sub 3, and the slope of this line is the average slope of these purple lines, okay? So you get improved Euler's method. We said it gets improved, you get improved accuracy, and it helps you a little bit better turning sharp or for volatile curves, okay? So this is improved Euler's method. All right, as you may have guessed, you can actually go further than this. Instead of finding the average of 2 slopes, you can find the average of 3 or 4 slopes. So the method that is loved by numerical analysis, it's a perfect method in terms of getting accurate answers and not having to use too many steps, okay? The method is named after two German mathematicians, Karl Runge and Wilhelm Katta. So it's called the Runge-Katta methods. I know this sounds vaguely Indian because of the, I guess Runge kind of sounds like Raj and Katta kind of sounds like Kolkata. But they're not named after Indian men. They're in fact named after Germans. So the Runge-Katta method, or the RK method, is a family of iterative methods, which include Euler's method and improved Euler's method. So Euler's method is known as the Runge-Katta of order 1, because you only find one slope. Improved Euler's method is known as RK2, or Runge-Katta of order 2. There's a Runge-Katta of order 3. We're going to go over the Runge-Katta method of order 4, which means we're going to find 4 slopes. Why? Because that's the most popular one that's used, because I think you get the most accuracy and you're not using as much steps. So it's a family of methods. There's others, and they are also named after groups of people. But the Runge-Katta is like a classic. Runge-Katta is a classic. All right. So, are you ready for this? Okay, I'm going to do my best. So, 4 slopes, and I'm only going to do one step, okay? I'm going to show you the jump from y sub naught to... All right, so we're going to look at a Runge-Katta method of order 4. All right, so here's my curve. I'm going to try to jump from x sub naught to x sub 1, okay? I have an intermediary point here. You'll see kind of why. All right, so the Runge-Katta method of 4th order uses 4 slopes. Here they are. The first slope is this line. It's the slope of this line. It's just the big F evaluated at x sub naught, y sub naught. The second slope is this line. It's big F evaluated at x sub 0.5, or x sub naught plus h divided by 2, and then y estimated with Euler's method, but for h divided by 2 using the previous slope. The third slope is f evaluated still at x, it's right here. It's still f evaluated at x sub naught plus h divided by 2, but the Euler's method is now estimated with, instead of the first slope, the second slope. And then the last slope, the 4th slope, is you're evaluating at x sub 1, x sub 0 plus h, and then this looks like improved Euler's method, and then y sub 1 is Euler's method for using the 3rd slope, okay? I know. And then it gets worse. Y sub 1, it's not actually the average of these 4 slopes. The middle slopes get weighted more. So it's the first slope plus the plus 2 parts second slope plus 2 parts third slope plus 4th slope divided by 6, okay? So that's how you get to x sub 1, y sub 1. That's the Runge-Katta method. RK4. All right. So, the Runge-Katta method of order 4 is given right here. You have to find 4 slopes, and it's big F evaluated at various x sub x's and y's, and then the next step is the weighted average of those 4 slopes plus your step, okay? All right. So what we're going to do